So today is lecture number 9 of this heat treatment subject, and we were in the middle of this discussion where we were talking about strengthening mechanism due to dislocations, or this is called strain hardening, also called work hardening, right? And if you people have remember this slide, we have seen that with increasing in the percentage cold work, the yield strength is increasing, the tensile strength is increasing, but the ductility is decreasing, right? We have seen that. Okay, and this is a very beautiful, you can say, very beautiful plot between this true stress versus true strain, where we have taken two metals, metal B and metal A, and you can see some difference here. So this difference you can see here, basically showing that different metal hardened differently upon strain, right? So due to strain hardening, different metal can behave in a different way. Some metals can be hardened more, some metals can be hardened less, right? So all of you might have a well knowledge on this equation. True stress is equal to K so you have, this is a relationship between the true stress with true strain, like this, sigma true is equal to K epsilon true to the power n, where n is the hardening exponent, right? And this hardening exponent, how to determine this? Hardening exponent can be determined if you take a slope in the plastic region. This region, if you take a slope, that slope will give you the hardening exponent. How much the value of n?
Sir, if we take the slope of the graph, which is of log sigma and log epsilon.
Yeah, you have to take in log scale, you are saying, right?
Yes, sir. In this
Hmm.
scale, that will not come.
Okay. So you can see the value of n here is 0.15 for some steels, and for copper it is 0.5. Okay, this part is over. The dislocation density. As this is strain hardening, this is work hardening. So you understand that on doing cold working on a metal or an alloy, we generate a lot of dislocations into the materials, right? A lot of dislocation will introduce into a material upon cold working, right? So that means the dislocation density is increasing in the materials, right? What is dislocation density? Basically, dislocation density is if you measure all the dislocation line length, so that is total length of all dislocation line per meter cube, or you can say total number of dislocation line per meter square. That is dislocation density. And which is denoted by this rho, right? Which is 10 to the 10 to 10 to the 14 meter per meter cube. So unit of dislocation density is meter to the power minus 2, obviously, because meter by meter cube, right? And if you have an idea that annealed metals which has undergone annealing process, there the number of dislocation density is less, basically below 10 to the power 10 meter per meter cube. But if you heavily cold work a metal, then the dislocation density is around 10 to the power 15 meter per meter cube, or meter to the power minus 2. Right? Here there is a very interesting example. Sugar cube size of a metal piece may have 1 lakh kilometer of dislocation line. It's very large. And how the strengthening is happening in this cold working process? Just this is a flow sheet of flow sheet is here. Cold working. If you do cold working on a metal or an alloy, what is happening? Introduction of lot of dislocation into lattice is happening. A lot of dislocation introduced into the lattice. So gap between the dislocation decreases, right? In the same slip plane. Suppose dislocations are on the same slip plane, so gap between the dislocation is decreasing. Then what happens? The strain field of the dislocation interacts with each other, right? Because around the dislocation we have strain fields. If you remember, they will start interacting with each other, then that leads to what? Some strain field repel, same strain field repel each other, leading to restriction, dislocation motion. The dislocation motion will be hindered or restricted. Hmm. And that leads to strengthening. So this figure is also showing the same thing. You can see this is one slip plane, this is another slip plane. You can see on this slip plane the dislocation is gliding. This is 1, 2, 3, and they have same sign, so they repel each other. If you introduce more and more dislocations, the gap between the dislocation will decreases. Obviously, if you introduce more dislocation here in this on the slip plane. Similarly, and the slip plane is here, dislocation are gliding. More dislocation introduction leads to more repelling nature, or due to this same strength field, right? So that leads to the strengthening effect. And another thing may happen like this. Suppose one slip plane is like this, and the slip plane is moving down here. They are intersecting one another. Suppose one dislocation is moving in this direction on this slip plane, and this dislocation is moving like this. Obviously, they will interact at the intersection point. So they get tangled up over there. So dislocation motion will be very difficult over there at the intersection point. So we need more stress, more shear stress we need for that. So that increases the strength of the materials, which is written over here only. We'll see that a very good relationship between the dislocation density and the distance between the dislocation soon. Okay, fine. You can see the property in this axis. We have property in this axis. We have cold work, percentage cold work. That means the percentage cold work is increasing in this direction, and the properties are shown over here. You can see with increasing in the percentage cold work, the yield strength is increasing, the tensile strength is increasing, right? But the ductility, which is shown by the reduction in cross-sectional area, is decreasing. Again, the ductility, which is shown by elongation, is also decreasing, right? Strength increases, ductility decreases with percentage cold work. Another interesting point here about the strain hardening is what? We can have some alloys which are heat treatable, and we can have some alloys which are non-heat treatable. It may be a steel, it may be an aluminum alloys, or it may be some other alloys, right? So heat treatable alloys, you understand. Okay, okay, anyways. Um okay, you people have heard about, anyways, transformation strengthening. Do you people have any idea on transformation strengthening? Strengthening due to phase transformation?
Yes, sir.
What is that?
जिसमें तो रिक्वेस्ट করছি ভাই
Martin
Yes,
Martensite
what is that?
transformation.
Martensite
Martensite
transformation,
and
very good.
Bainite
Bainite transformation, very good, very good. So austenite will transform into martensite or bainite. Huh? Those are which kind of products? Basically, equilibrium or non-equilibrium products?
Non-equilibrium.
non-equilibrium.
Non-equilibrium products. Why they are called non-equilibrium products?
Because of fast rate of cooling.
Because of fast rate of cooling. Very good. Because due to non-equilibrium cooling. Non-equilibrium cooling means very fast rate of cooling, like quenching you are doing, for example, right? So if you differentiate between equilibrium product properties and non-equilibrium properties, non-equilibrium product properties, what is the difference? If you compare the properties between the equilibrium product and non-equilibrium product, what is the difference?
Strength.
Yes, what is the difference? Yeah, strength. What do you mean by strength here?
In non-equilibrium product, the strength is more.
Very good. In non-equilibrium product, the strength is very high. Okay, compared to equilibrium products. What? Anything else?
Grain size.
Grain size. Very good. Grain size. So basically, non-equilibrium products or non-equilibrium transformation products are finer, basically, as compared to that of equilibrium products. And the one is that they are stronger and harder. Basically, the phases are stronger and harder as compared to the equilibrium products. Okay, very good. You have remembered that. So here the point is what? Heat treatment, as I told, heat treatment is a technique by which we can go for transformation strengthening. You have to remember that. Heat treatment provides transformation strengthening. One kind of strengthening heat treatment provides is grain refinement. That is one part. But apart from grain refinement, by doing heat treatment on metals and alloys, we can have transformation strengthening. Due to phase transformation, a strengthening is coming out. So this kind of transformation is a solid state transformation or liquid to solid state transformation?
Solid state.
Solid state.
Solid state, very good. Austenite will transform into either martensite or benite, right? All are solid phases. Very good. And heat treatment itself is a solid state process. Huh? You have to remember that. Okay, you can see by doing heat treatment on certain alloys, we can have non-equilibrium products like martensite or benite, or we can have some precipitates, secondary phases. So strengthening will be there. But if the alloys are non-heat treatable, that means they are not showing any response to the heat treatment. There is no precipitations, there is no formation of equilibrium products, basically, right? Or basically, you understand there is no formation of precipitates, for example, right? So in that conditions, we can increase the strength of the metal or alloys by this strain hardening method. Simply we take that particular alloy and we will deform it plastically. The moment we deform it plastically more and more, the strength will increase, right? So you have to remember, this is very interesting. Many people ask this kind of questions. Suppose somebody may ask like this, ki I have an alloy which cannot be, which is not showing good response to the heat treatment. So what can be done to increase the strength? Just the answer is just do cold working on it. That's all. If you deform it plastically below the recrystallization temperature, the number of dislocations will increase, and that will harden the materials, right? I think you people have understood now, right? And the point is the rate of strain hardening. You can see if we have FCC metals or FCC alloys, basically, they get more hardened. The rate of strain hardening is more in FCC metals than as compared to that of HCP. Can anybody tell me why this is happening?
Sir, SCP is more ductile.
FCC is more ductile. That's why.
HCP is ductile.
HCP is a ductile. You have gone through the IPM notes. Have you gone through the IPM notes? How many number of slip systems are there in HCP?
3.
How many slip systems are there in HCP?
In HCP,
I'm talking about in HCP and FCC. Okay, Panda, can you repeat what you told about HCP or FCC?
face
HCP.
You
centered
are
has
talking about
12
HCP,
and
yes.
hexagonal has 3.
Yes, very good. So HCP metals basically have 3 slip system and FCC has 12 slip system. So if the slip system will be more, so what will happen? Which one will be more ductile?
More slip
FCC.
systems, FCC.
Obviously FCC, because slip system means it is a combination of what? Direction and planes, right? Slip direction and slip planes, where dislocation motions will be easy, right? Or the atomic movement will be easier in that condition. So now, so Panda, you got the point where you are making a mistake.
Yes, sir.
Yes. So basically what happens, since FCC have more slip systems, so more dislocation can be generated in the materials. Because more deformation will be easier and more dislocation will generate. So the rate of strain hardening will be more in case of FCC as compared to that of HCP. I'm talking about the rate of strain hardening. This statement is important. Okay, can anybody tell me why in hot working strain hardening do not occur? What may be the reason? Everybody know about what is hot working, right? Obviously, you people know. Just use your mind. What may be the reason? How many of you have remembered the annealing on cold work metal?
Sir, there are new strain-free materials developed. So
Sorry, can you repeat? Your voice is not clearly audible.
sir, new strain-free materials are created there.
Strain-free metals are created there. Okay. Anybody want to speak anything? Why in hot working strain hardening is not? Strain hardening is often due to your cold working, not hot working. So why? Why hot working will not show any kind of strain hardening? Because you understand, hot working means the working is done above the recrystallization temperature. The temperature is very high. So what will happen? Lot of vacancy will generate, right? At high temperature, lot of vacancy will generate, and lot of vacancy generation will lead to diffusion of vacancy and atoms, right? Temperature is also high. which is favorable for diffusion, right? So what will happen? The dislocation will get climbed. The climbing of the dislocation will be happening, and it will get absorbed by the grain boundaries or the surface of the materials, basically. So there will be annihilation of dislocation will be happen. You understood now? There will be annihilation of dislocation. Dislocation will get disappear due to high temperature, due to diffusion of vacancies and all. So strain hardening will be not there, because strain hardening means dislocation interaction is happening over there, right? Strain field of one dislocation is interacting with the strain field of another dislocation. That is why they are restricting the motion of one another. Okay, next one is, yeah, this is a very good figure. Everybody have to remember this one. This figure, you can see this is the strength axis. Strength is 0 and strength is increasing like this. Here, dislocation density is 0 here, and dislocation density is increasing in this direction. Fine. So strength versus dislocation density. So you can see the plot starts from here. The plot starts from here. You can see this is the starting part. You can see that means when there is, you can imagine just there's 0 dislocation density in a material. When there is no dislocations, then the strength of the material is G by 2 pi, which is nothing but the theoretical shear strength of the materials. Which kind of materials have strength equal to theoretical shear strength?
Single
Sir,
crystal.
whisker.
Single crystals, viscous, very good. Single crystal or viscous. Why they have theoretical shear strength?
Due to
In the
absence of any
first,
dislocation and grain bound.
very good, very good. In the starting part, I told you, right? If you remember, yes, very good. So we do not have any dislocations, we do not have any defects. We do not have any crystalline defects, right? Or lattice defects. No grain boundary, no dislocations. So strength is nearly equal to theoretical shear strength. So G by 2 pi, shear modulus by 2 pi, right? This is very high. Some gigapascal level, gigapascal. So you understand when we have a 0 dislocation in a material, strength is maximum. But the moment the number of dislocation is increasing, the strength is going down in a materials. It is going down with number of dislocations. It is going down, 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 and this to a minimum value. This is the lowest strength possible here. When the dislocation density is this much. But again, when the dislocation is increasing further, more and more and more dislocation is getting introduced, the strength is again increasing, you can see. Right? So this is the contradict point, very good, right? Initially, with increasing in the dislocation, the strength is going down, but after some times, when the dislocation density is very high, the strength is again increasing here, right? So suppose I will give, this is a common question to everyone. Suppose I will give you 3 samples. One sample is a single crystal, and the sample is having, another sample is an annealed crystal, and the sample is a heavily cold work crystal, right? So can you people arrange them according to their decreasing strength? First sample is single crystal, second sample is annealed polycrystalline material, and that sample is your heavily cold worked polycrystalline sample.
Sir, annealed fast
Single crystal.
Annealed will be having high strength. Okay, Barik is saying annealed
Yes,
will
sir,
be having high
annealed,
strength.
sir, low dislocation density.
Annealed will be having high strength, you are saying, right?
No,
Yes,
sir. Annual
Soumya.
will have low
No, sir,
strength.
Okay,
annealed low
let
strength.
Soumya, allow Soumya to speak. Yeah, Soumya, yeah. What you are
Sir,
saying?
annealed ସବୁଠାରୁ low dislocation density ହବ, low strength.
I
ତାପରେ
am not
ଆସିବ
asking about the density. I am asking about arrange the samples according to decreasing in strength.
annealed first.
Annealed have high strength. Okay.
Sir, annealed have low strength. Sir, low ରୁ high କହୁଛି.
I am asking about you have to arrange the samples according to decreasing order of the density strength. Strength will decrease.
First single crystal,
Okay, single crystal, then
cold work,
cold one.
then annealed.
Okay, fine. Very good. So you people have understood this plot. Very good then. Anyways. So now you can see there is a relationship between the shear stress and dislocation density. You can see this is a very good relationship. Tau is equal to kb root over of rho. So here the shear stress required to force two dislocation past each other. the shear stress required to force the dislocation past each other is depending upon the dislocation density. So if you have a heavily cold work metal, so shear stress required will be more or less, so that dislocation can cross each other or past each other.
More.
Obviously more. This is there, because there is a direct relationship here. Very good. You understand, this is a B for Berger vector. This is a constant, and this is dislocation density. Okay, next is yeah, this is a very interesting point again. This there is a relationship between L and dislocation density. L is nothing but the space between two dislocations. The space between two dislocation. The space between the dislocation is denoted by this, and this is the dislocation density. There is a relationship. So you understand, I can write it like 1 by square root of dislocation density, or L is inversely proportional to dislocation density. So you understand, if we have more number of dislocations or dislocation density is higher, what happens to the spacing? Will be less. If the spacing will be less, obviously the strength will increase after some times. So then okay, this is an interesting point again. Basically what happens when the number of dislocation increases in a materials, they basically, okay, this is a very interesting part here. Suppose we are deforming a metal more and more. We are doing cold working. The percentage cold working is increasing. That means we are increasing the number of dislocations. When the dislocation increases, they contain strain energy, right? So a lot of strain energy will be there inside the materials, but materials do not want that. So what happens? The dislocation try to arrange themselves in a particular structure or particular fashion. They try to arrange themselves. So that leads to formation of the dislocation cell, formation of cell wall. Formation of cell wall. Dislocation actually arrange themselves in a cell form. So suppose this is totally a grain. This is a total single grain is there, right? And these are the dislocations. Dislocation I have arranged them as a form of cell. So these are dislocation cells, like grain inside a big grain. Or these are also called substructure. This kind of substructure is formed because dislocations will arrange themselves in such a fashion that the strain energy will reduce in the material. And here another figure is there. Only 10% of the cold work energy is stored in the materials. Rest of the energy will get lost in form of heat and sound like that. Okay, now source of dislocations. Dislocation source is called Frank-Reed source. Already you have studied this one, I think. Again, we will discuss here. You can just look at this figure. This is a very interesting figure. You can see this A, this is B. These are two particles. This is one particle, this is another particle, right? These particles may be your precipitate, this particle may be any dispersoid, or this may be any inclusions, you can say, right? So these two particles are having a space between them, right? Like this. And this line is a dislocation line, dislocations. So dislocation, suppose, is present over here, and it is moving in this, gliding in this direction. But the moment it will come to this point and this point, this will pinned. So this two particle is pinning the dislocation. So this is one, first stage. First stage of dislocation multiplication or dislocation formation. This is stage one. Next, what will happen? Still, till now the stress is there. This one tau is acting on the dislocations, but dislocation cannot move, but it can bow. So dislocation is bowing like this. So this is the stage two. But still the stress is acting on the material. So what? Dislocation bow like this. This is the third stage. Again it will bow. This is the fourth stage, like this. But now what happens when the bowing is up to this extent, fourth stage, this one, you can see this is one end of the dislocation, this is another end of the dislocation. Actually, this is, suppose, this part of the dislocation actually is opposite sign to this part. Or this part dislocation is having opposite sign to this part. Or this is, suppose, upright dislocation, this is inverted dislocation. So what will happen when two dislocation are of opposite sign? What happens to the dislocation? What happens to the dislocation when two dislocations are of opposite sign?
Annihilate.
They annihilate. How they annihilate? Simply they will annihilate,
So
or they will do
tensile
something so
and
that they will get.
compressive strain, the field.
So they will attract, na, first.
Yes, sir. After that, they will
They
annihilate.
will attract and they will come closer, and finally they will get annihilated, right? So same thing will happen here. They will attract and they get annihilated. So upon annihilation, the final structure is what? A dislocation loop. You can see this is a dislocation. This is the fifth stage. A dislocation loop will form. This dislocation loop will be around these particles, and a dislocation will come out from that. A straight dislocation will come out from that. Fine. The same figure I can explain over here. You can see this one. This is the stage one. This is a dislocation line. It is moving in this direction and getting pinned up by these 2 points. But shear stress is still acting on it. So it will go like this. Further, it will go like this. Third stage. In fourth stage, it will go like this. This is the fourth stage. And you can see opposite sign dislocation here. This part is opposite to this one. Finally, they will get annihilated, and finally a dislocation loop will be forming here. And one dislocation will come out from that. Maybe I have some, let me see. I have some dislocation glide. Okay. No, sorry. Okay. I think I have a video to show you how dislocation multiplication is happening. This is the dislocation glide. Okay. You people want to see a dislocation gliding? If you want, I will show you a video.
Yes, sir.
Okay, you want to see a video? Okay, let me show you then. Okay. Now I think the video is visible to everyone.
Yes, sir.
Okay, just have a look how dislocation are gliding in a materials. This is a very interesting video. Just look at the videos. This is actually real video, which is taken with the help of a transmission electron microscope. You are seeing how dislocation are moving, gliding. Okay. Okay, fine. This is over. This is over now. Okay, fine. As I have told, what happens during cold working? Just look at over here. What happens during cold working? The strain in the material increases, the dislocation number increases, the ductility decreases, and strength increases. So these are the things which will happen during cold working on a metal or materials, right? But after cold working, suppose still you want to deform a metal. So it is not possible due to strain hardening, right? So you can do annealing process. So annealing, upon doing annealing process is a kind of heat treatment process where we require heat, high temperature. So what happens during annealing? Strain will go down, dislocation number will go down, ductility will increase, strength will go down, right? If you talk about any physical property like electrical conductivity, if you remember in IPM class, electrical conductivity goes down in cold working, but in annealing process, electrical conductivity again rise, right? So these are the things will happen in annealing, right? Which can be explained. I will explain it soon. You can see. So in annealing process, when we are doing annealing on a cold work metal, what we are doing basically, we are rising the temperature of the metal slowly to a high temperature, right? So 3 stages are there. One is recovery stage, another one is recrystallization, and finally is the grain growth. So first is that means at the low temperature we have, this is the very good image you can see. In this direction temperature is increasing. This is the increasing in the temperature direction. And what is happening? It is shown over here. So at low temperature recovery is happening, and at intermediate temperature recrystallization happens, and at a high temperature grain growth happens, right? So what is happening? You can see tensile test is going down, but the ductility is increasing, right? So what exactly, if you remember what is recovery, in the recovery stage what happens? The metal recovered to its initial values, initial data, like it ductility once again come into the picture. You can see your electrical conductivity is coming into the picture, which has been lost during the cold working process. So restoration of physical property, that means of the cold work metal, but there will be no change in microstructure. In recovery stage there will be no change in microstructure, but again what happens? And some people are saying due to temperature existence, vacancy generated in the material, and that helps in the diffusion of vacancy. So dislocation leads to dislocation climb and get annihilated at the grain boundaries. So these are one of the things which may happen during recovery. That it is already written, like dislocation get annihilated, and unlike dislocation, tilt boundaries will form to lower down the strain energy. Then what happens? The recrystallization. Recrystallization is the formation of new strain-free crystals or defect-free crystals from the existing strain grain, right? And grain growth means new strain-free grains formed, start growing and become bigger due to high temperature prevailing, right? So these are the things which will happen. I'll show you some very good images. Just look at, suppose this is a heavily cold work metal. So you have to tell me, we will discuss here, right, quickly. So this, if this is a cold work metal, what you can able to see here? In a heavily cold work metal, what you can able to see?
A lot of edge dislocations.
A lot of edge dislocation are present. All have same sign or different sign?
Different sign.
Different sign. Okay, fine. So what is this figure is showing? Can anybody tell me this figure and this figure? What is happening when the temperature is increasing slowly? Just look at this one and this one.
Coming nearer to each other.
Yeah, they are gliding. Dislocation are gliding,
Yes,
and what is happening? Just look at this figure and compare
Annihilation.
this figure with this figure. Annihilation is happening. Very good. Annihilation is happening. Very good. Which dislocation get annihilated?
Edge dislocation.
Okay, obviously edge dislocation, but which dislocation?
Unlike
Positive and negative.
Unlike dislocations, very good. With dislocation, opposite sign. Can you people look at where it is getting annihilated? This portion you can see, this one, here, and this point. This is another figure, right? Here you can see this one, here. Okay, and can you tell me what is the meaning of annihilation here? Annihilation exactly means what?
Sir, they
These
are
half planes,
cancelling their effect.
Cancelling their effect? Don't tell
sir,
such things.
these
Cancelling
half
effect.
planes
Yes.
come together and make a full plane.
Full plane, very good. It is now, there is no extra half plane of atom. Now this is a
Sorry.
complete plane of atom. Very good, very good. I think everybody have understood. This is now a complete plane of atom. This is not an extra half plane of atom now. Complete plane of atom. Anyways, finally, what this figure is showing? This one and this one finally.
Sir, a lot of dislocations, edge dislocations again, but same sign, positive
Yes,
axiom.
same sign. Lot of dislocation, same sign. What they are doing?
Sir, tilt boundary,
They are forming a tilt boundary, but what they are doing?
annihilating.
Annihilating. I'm asking, what about this figure and this figure? What is happening? Compare this figure with this figure and this figure.
They arrange themselves in a particular fashion.
Very good. They have arranged themselves like, one above another or one below another, right? Everybody can see all are like dislocations. So unlike dislocation are getting annihilated during recovery, but like dislocations, they are arranging themselves in a particular fashion. They are arranging one below another, right? It is clear now. This kind is called polygonization, if you remember. How many of you have remembered polygonization? Nobody have remembered this term? So this happens during recovery stage basically. And formation of tilt boundary. You can see this is a tilt boundary. So that means this is a small grain. You can say this is a small grain, or this is a small grain, this is a small grain, or grain with low angle grain boundary. You can see this is a tilt boundary. Because you can see initially this is like this single grain, but due to arrangement of dislocation like this, we can have small grain inside, sub grains you can say. This is a tilt boundary here. Dislocation glide picture you have seen. Now we'll just look at this image. Which kind of grain is this? Just tell me quickly. Let me see you can answer. Which kind of grain structure is this? Which kind of grain structure is this? Nobody is saying.
Undeformed.
It's undeformed. That is fine. But structure. What is the structure of this grain? Do you people remember when I was talking about those solidification part in IPM? Upon solidification, what kind of grain structure you get?
Sorry.
When you are doing
Equiaxed and columnar.
Equiaxed.
EQX, yeah, somebody has told EQX. Who told? Biswajit. Biswajit, I think. Biswajit, you are.
No,
yes.
sir. No, sir. No, sir.
Who told EQX?
Sir, I told equiaxed and columnar during solidification.
During solidification, EQX and columnar grain will be there. That's fine. But in what conditions? How many of you have remembered? Let me see. If you are not adding any kind of inoculants into the molten metal, which kind of structure you will get? And if you add
Columnar. Sir, if
But-
we add any alloying element, we will get equiaxed, that is heterogeneous solidification.
Very good, very good, very good. Not alloying element, basically it is not alloying, inoculants, which will
Nucleating
act as
agents.
a nucleation sites. Nucleation will be happening everywhere, right? In the molten metal. That will give rise to equiaxed grain. But absence of nucleating agent or inoculant gives rise to which kind of structure? Macrostructure in solids.
Equiaxed.
Absence of inoculants.
Columnar.
You are just guessing. Just tell me clearly.
Sir, both columnar and equiaxed.
Yes, both columnar and equiaxed. Very good. Where it will form columnar and where it will form equiaxed?
At the wall,
Sir, at
wall
the
columnar
boundary,
and at the
equiaxed.
center equiaxed.
Oh God! At the wall, it is columnar. Are you sure? Do you remember the figure I have drawn in the blackboard?
So at the wall
Sorry,
it is
green board.
equiaxed, and towards the center it is columnar.
You people have forgotten everything. Just look at the image today. Go and check your IPM notes at least. You have a mold wall, so mold wall will act as a heterogeneous nucleation site. Nucleation will start over there, but the nuclei form is basically small and equiaxed one. Very small and equiaxed. After that, what happens? Since the heat is getting transformed from the center to the outward direction, columnar grain will form. Columnar grains, which are like a columns toward the centers. But after sometimes what happened? At the center of the mold, again equiaxed, big size equiaxed grain will form. Now you got the answer? Please go through the IPM note at least. We'll get the answer. So this is a which kind of grain? Now equiaxed grain. So this is what? This is rolling. I'm rolling this material. What is happening to the materials? What kind of grain we have? What kind of grain is this? Nobody is saying. What kind of grain structure is this? What kind of grain structure is this? This one equiaxed. What kind of grain structure is this?
Extended,
Yeah, elongated grains.
elongated.
Elongated grains. In which direction they have elongated?
Metal flow direction.
Yes, metal flow direction or rolling direction, where we are doing rolling on this. These are rollers. This is one roller, this is another roller. Okay, fine. So after that means this is now cold working. I'm doing suppose cold working. After doing cold working, I'll then if I'll heat it, recovery will happen. In the recovery stage, what happens? You understand? Annihilation of dislocation is happening. Many defects will get annihilated, but still we have a lot of dislocations in the materials, right? So when you heat it, this is a coil. This is a coil. So just can anybody figure it out what is happening in these materials now? Just look it carefully in this region. What is happening?
Fine grain, sir.
Just look at this one and tell me. Yes.
Recrystallization.
Recrystallization is happening. Very good. Small, tiny grains are forming along the grain boundaries and where there is lot of dislocations. You just look at this image. Finally, what is happening? You will end up with what? This one. What are these? What are these?
The new strain free
Final
grain.
grain.
New strain-free grains. What is the structure?
Equiaxed.
Equiaxed. Very good. Again, equiaxed. That means from this elongated grain, upon recrystallization, you are getting again equiaxed grain, which is strain-free. There is no strain. That means you can consider it is defect-free, or you can consider this is not having dislocations. But still, it has dislocations. It is not like all the dislocation will get removed. But comparison to this number of dislocation and over here, it is very low. Next is finally, just look at this figure. Still, you are heating it. You are taking to a very high temperature. So what is happening? These are the equiaxed small grains. What is happening to these grains? Just look at this one.
Grain growth.
Coarser grains are forming.
Yes, grain is becoming coarser, right? A coarser grain have low ductility, if you remember, or high ductility. Coarser grain have high ductility or low ductility?
High ductility.
Very good, high ductility. Very good. So, okay, fine. And this is a figure showing your two stress versus strain plot, engineering stress versus strain plot for ferritic steel and austenitic stainless steel. Ferritic stainless steel and austenitic stainless steel. So you can see this is getting more strain hardening effect here. And there is an interesting point. Strain hardening is not often used as a strengthening mechanism in all steel product. All steel products are not strain hardened because it reduces the plasticity in the materials. That is the reason. So corrugated galvanized roofing sheets are strengthened by deformation. This is one of the examples where we are giving a metal steel strain hardening effect. That is corrugated galvanized roofing sheets. You have seen this kind of sheet on the top of the roof. How to determine how many dislocation density is present? So by using TEM or by using XRD. In XRD, we can have a big broadening. Yes. So by using XRD, X-ray diffraction analysis, or by using transmission electron microscopy, you can able to find out how many dislocation density we have. But this is a very difficult job. Another interesting point. Some may ask you, what is the one of the cause for strengthening of martensite? So one of the major cause of strengthening in martensitic structure is due to high dislocation density in the martensite. You have to remember that. Everybody have to remember that. Whenever we have a martensitic structure, we have a high dislocation density in the martensite. That is one of the reason why we have high strength or high hardness. Because it is written over here. One of the reason behind high hardness or strength in ferrous martensite, basically I'm talking about ferrous martensite. Martensite can be formed in other titanium alloys or other alloys also sometimes. My microstructured steel is due to presence of high dislocation density. This number of dislocation density can be achieved by huge plastic deformation in pure alpha iron. Okay. Martensitic transformation requires shearing the lattice, and shearing is accomplished by transformation dislocations. Okay. I'll end this topic here. We'll complete the strengthening mechanism in next class, where we'll discuss about precipitation strengthening and dispersion strengthening. Right. Okay, if you have any doubt, you can ask me right here. Otherwise, you can call me up.